In 2018, a robot taught itself to walk from scratch, with zero human programming, in about 2 hours. Then, weeks later, doing something completely unrelated, it forgot how. And the reason why is one of the strangest, most underreported problems in all of AI. This isn't science fiction. This actually happened in a lab with a 4-legged robot called Minitaur. Researchers at Google and UC Berkeley. No simulation. No pre-programmed walking gait. Just raw trial and error directly in the real world. At first, it was chaos. The robot flailed, face-planted, dragged itself sideways. Every failed attempt fed data back into its neural network, a system that adjusts itself a little after every single try. Within about 2 hours, faster than most humans learn to parallel park, Minitaur had a stable, working gait it invented entirely on its own. Nobody told it how to balance. Nobody showed it a diagram of a walking cycle. It found the answer through pure trial and error, the same way a toddler does, by falling down a few hundred times and quietly getting better at not falling down. And this wasn't a one-off fluke. Other teams pushed it even further. Researchers at Berkeley later built a robot that learned to walk in about 20 minutes flat, version of the same idea. Within 5 minutes, it could shuffle forward. Within 10, it was taking real strides. Within 15, it had learned to balance while doing it. Robots that used to take weeks of careful hand-tuning were now picking up walking almost as fast as you could watch a video explaining it. That part of the story gets all the headlines. The part that doesn't is scarier, and it has to do with how these systems are built in the first place. Here's the catch. The brain behind Minitaur, and basically every AI system like it, is a neural network, a giant mathematical structure made of millions of adjustable connections. When it learns something, those connections get nudged slightly to make the correct behavior more likely next time. That's the entire mechanism behind how it improves. But that same mechanism has a nasty side effect researchers call catastrophic forgetting. When a neural network learns something new, it doesn't file the new skill away in a separate folder next to the old one, the way you might save a new document without touching your old ones. It overwrites the same shared connections the old skill was using. Teach it a new terrain, a new task, a new environment, and the very same update that makes it good at the new thing can quietly erase its ability to do the old thing. Not gradually, like slowly forgetting a phone number. Catastrophically. Sometimes within a single retraining session. And this isn't some obscure edge case buried in a footnote. It's one of the most studied failure modes in modern machine learning. Continual learning researchers have documented this exact pattern across robotics, translation systems, image recognition, basically anywhere a neural network keeps learning after its first task. There's actual published research on robot manipulation arms trained to solve one task, then retrained on a second, related task, and the retraining wipes out the first skill almost entirely, even though nobody deleted a single piece of data. The knowledge wasn't erased on purpose. It was overwritten as a side effect of getting better at something else. Now apply that to a walking robot. The skill of how to balance on 2 legs on flat ground, and the skill of how to climb a slope, might rely on overlapping pieces of the exact same network. Push the training too hard toward one, and the other can quietly degrade in the background. There's no warning light. No error message. The robot still walks. It just doesn't walk quite right anymore. Maybe it stumbles on terrain it used to handle fine. Maybe its balance gets subtly worse in ways that only show up under stress. The forgetting is invisible until you specifically go back and test the old skill again. This is exactly why just let the AI keep learning on its own is way harder than it sounds. and why almost nobody deploys these systems the naive way in the real world. This is one of the biggest open problems in AI right now, and it's not limited to robotics. Every large language model, every self-driving car system, every AI that's supposed to keep improving after it's already deployed runs into some version of the same wall. Retrain a model on new data, and you risk quietly degrading its performance on things it used to be great at. Companies have to constantly retest old capabilities every time they update a model, specifically because updates can silently break things that already worked. Here's the part that makes this genuinely strange to think about. Humans barely have this problem. You learned to ride a bike as a kid, and you can probably still do it decades later without practicing once. You learned to read a clock, tie your shoes, recognize your childhood friend's face, and you kept all of that while learning thousands of new things on top of it. Neuroscientists think this is because your brain runs something like a dual memory system. Fast learning happens in one region, while another region gradually and carefully protects older, well-established memories from being overwritten. Most current AI systems don't have anything like that built in by default. They're single systems where new learning and old learning are fighting over the exact same real estate. So how are researchers actually trying to fix this? There are a few serious approaches being tested right now. One is called elastic weight consolidation. The idea is to mathematically figure out which specific connections in the network matter most for an already learned skill, then essentially lock those connections in place, making them harder to overwrite while the network learns something new. It's like putting protective tape over the parts of the wiring you don't want touched. Another approach is called pseudo-rehearsal. Instead of protecting the connections directly, the network periodically generates and replays synthetic examples of the old task while it's learning the new one, essentially quizzing itself on the old material so it doesn't slip away. It's not unlike flipping back through old notes while you're studying for a new exam, just to keep the earlier material fresh. Both approaches genuinely help. Neither one fully solves the problem. This is still an active, unresolved area of research, which means every robot, every AI assistant, every self-driving system that keeps learning after it leaves the lab is dealing with some version of this trade-off, right now, in the background, whether anyone talks about it or not. So the real story here isn't just robot learns to walk in 2 hours, remarkable as that is on its own. The real story is that teaching a machine anything new, at any point after its first lesson, carries a quiet risk of costing it something it already knew how to do. We've gotten remarkably good at building AI that learns fast. We're still, genuinely, figuring out how to build AI that remembers. If that trade-off unsettles you a little, that's the right reaction to have. Subscribe if you want more deep dives into the strange, under-the-hood edges of AI that most people never hear about. And let me know in the comments, should AI systems be allowed to quietly forget things in order to keep improving, or should we be forcing them to remember everything, even if it slows them down?